8.6, comparing linear, exponential, and quadratic functions. So here we've got the standard form of these three types of functions, and we've also got what they look like. So, you know, a linear function is going to be a straight line, quadratic function is going to be a parabola, and an exponential function will be a curve that looks something like this. So on this first set of problems, all we're going to do is plot a set of points and try to decide, does it look like one of these three types of functions, okay? So let's go ahead and do that. So on this first one, let's see, I'll zoom in a little here. We've got -1, 5, that would be up in this top left corner. 2, -1, 2 to the right, 1 down, 0, -1, 3, 5, it's right up here, and 1, -3. And then, hey, to me, that looks like a parabola would fit that pretty well, right? It looks like you'd have kind of a U shape. So this looks quadratic to me. Because, yeah, you could fit all those on a parabola. You'd have a hard time fitting them on a line or an exponential curve, okay? So this one is going to be quadratic. Okay, let's try the next one. So let's see, -1, 2, -2, 8 is in that top left corner, 0, 0.5, and then 1, 1/8. So that's just barely above the x-axis there. And to me, that looks like it would be an exponential curve. This curve is going uphill, this one goes downhill, but this still fits, looks like it would fit a curve. I guess you could make an argument that it might look sort of like it could fit on a parabola if we had more points to the right, but just with the points that we have, it looks to best fit exponential. Okay. And then let's try another here. -3, 5 is up here. 0, -1. 2, -5, -4, 7 is in that top corner, and then 1, -3. Well, that doesn't look like it curves at all. It looks like a straight line would fit nicely through those, right? So that means that this those appear to fit a linear function. Okay, on the next page, we're going to look at common differences. Okay, so we've got some XY tables here, and our goal is going to be to figure out, would all these points, if you plotted these points, would they fit on a straight line or a parabola or an exponential curve? And you could plot them out to make a determination like we did on the previous page, but you can also do this without graphing by doing a little test, okay? Now, in order to do this test, you need the x's to be evenly spaced. So the x's have to be evenly spaced. It doesn't have to start at 1 and be counting by 1s. It could start at 50 and be counting by 10s. So this could say 50, 60, 70, 80 for the x's, something like that, okay? But I do need the x's evenly spaced. And if you've got a common first difference, that means you're going to have a linear function, or at least that your points would fit on a straight line. They would fit on a linear function, okay? And the common first difference, when these x's are evenly spaced, I want to look, well, what am I adding or sometimes subtracting to get from y term to y term? So I'm thinking 2 plus something is 4, that would be 2. 4 plus something is 6, that's 2. 6 plus something is 8, that's 2 as well. So since I got the same number out, I'm making the same jumps to get from y term to y term, that means I have a common first difference, and that means that I've got a linear function, so that these points would fit on a straight line, okay? If I try to do that same test on this next XY table, well, let's look at the first differences here. So I'm thinking, what kind of jumps am I making? 1 to 4, I'd be adding 3. 4 to 9, I'd be adding 5. 9 to 16, I'd have to add 7. And 16 to 25, I would add 9. I don't get the same number out every time, so that means that this is not going to be linear. If I plot those points, they will not fit on a straight line. Okay. So what we can do then is we can check what's called the second differences, all right? And this is going to fit on a parabola if the second differences are the same from number to number. And what the second differences are, you look at your first differences, and we're going to look at the jumps between those, okay? So 3, 5, 7, 9, I'm counting by 2's here, right? So I'm adding 2 to get from one difference to the next, and so that means that this is going to be quadratic because the second differences are common because I get the same number out every time, okay? So this is a first degree equation, linear. Quadratic is a second degree. So you could actually look at the third differences to see if it would fit a cubic function and so forth, and even fourth or fifth or sixth or seventh degree if you had enough ordered pairs to check. But we're only going to go up to quadratic for looking at the differences. Okay. On the next XY table down here, if you're looking adding to get from term to term, I'm not going to write this down, but it would be 3, and then you'd have to add 6, and then you'd have to add 12. Okay, so it wouldn't be first degree, and if you looked at the second differences, those wouldn't come out the same either. But there is a pattern with the y's. So the x's are evenly spaced again, okay? And if you look at this pattern, the y's are doubling, right? So we can multiply by 2 going down the line. So we're multiplying by the same thing to get from term to term. That means we've got a common ratio, and that means that this is going to fit an exponential function. So these points would all fit on an exponential curve, okay? So that's what goes in the blank here. Should have written that first. Okay. Okay, so those are the tests that we can do. All right, so let's go ahead and try it out on some XY tables here. Okay, so we're supposed to decide linear, quadratic, or exponential. Okay. All right, so let's take a look at this one. So first we'd be, if we're looking at adding, let's see, we'd add 2 and then 6. When these numbers get bigger, or if you have decimals or something, you can, I'm thinking 9 plus something is 27. Well, you can just work backwards. Take any number like the 27 and subtract the previous term from it, and that tells you 9 plus 18, right? And then I can do 81 minus 27. That'll tell me 27 plus something equals 81. So, okay, so it's not linear because those first differences weren't the same. And then we can check, well, is it quadratic? Okay, and let's see, 54 minus 18, that's going to give me 36. So, hey, it's not second degree either. It's not quadratic. So I'm thinking it's probably going to be exponential since those were my only options. But let's test it out, okay? So I'm going to rewrite the y's here just because I already wrote underneath them. And I'm going to think, well, am I multiplying by the same thing to get from y term to y term? 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27. And 27, if you try it on your calculator or just by hand, 27 times 3 is 81, so that means, hey, this is going to be exponential because I got a common ratio here. Okay, let's try another out here. So looking at adding first, let's see, we'd add 12. 15 plus 20 would be 35, and let's see, 63 minus 35 is 28. Okay, now, that's not linear because I don't have a common first difference. Let's check the second differences. And hey, we're adding 8 to get from, we do have a common second differences. That means these points would fit a quadratic function. So they would fit on a parabola if you graph them. Okay. And then let's see, first differences here. Oh, by the way, so you can see that the x's are still evenly spaced on all these, right? Because we're counting by 3's here, we're counting by 2's here, counting by 1's on the first one. Okay. But my y's here, we're adding 5 to get from term to term. We're counting by 5's for the y's, so that means we've got a common first difference, and so those points would all line up in a straight line and fit on a linear function. All right, that's the end of the section, and I'll see you next time.